Hi, the next section, 5.4, the competencies. So unlike the previous three sections, we test the variance. So suppose that we have the x and y, and we have several observations for each, and if x and y may have different expectation and also may have different variances. And we want to compare the sigma x and the sigma y. So the null hypothesis is sigma x square is equal to sigma y square, and alternative is sigma x square is not equal to sigma y square. Of course, we can test also the sigma x square is less than sigma y square, or sigma x square is larger than sigma y square. And test statistic is this f. So in the testing, usually we construct a test statistic, then we calculate p-value, then we decide whether or not we reject h0. And f statistic is sample variance of x divided by sample variance of y. And this follows the f distribution with df n-1, m-1. So n-1 is numerator degrees of freedom, and m-1 is denominator degrees of freedom. And remember that the f random variable is defined by sum of x1 square to x n-1 square divided by n-1 divided by y1 square plus up to y m-1 square divided by m-1. So this random and this here, the xi's and yj's are all standard normal random variables and independent. Then this random variable f is defined as the f random variable with degrees of freedom n-1 and m-1. So you can see the denominator and numerator of this f is similar to the definition of variance. And basically, the f statistic is centered around 1. So that means the numerator and the denominator both have expectation of 1. So I don't say the expectation of f is 1, but the numerator and the denominator is approximately 1 because everything is square of standard normal. So expectation of standard normal is 1. That is variance, so that is 1. And we add n-1 terms, then divided by n-1. So approximately expectation is 1. The numerator also the same. So f distribution is skewed distribution of this shape. The shape also depends on m and n, but roughly speaking, this is the density function of f. So using this theorem, then we can test this h0 against h1. And p-value is calculated by this formula. This is a little bit intuitive, unintuitive, so that we explain with a graph. So basically, that we have f distribution here. This is density function of f distribution with df n-1, m-1. And once you observe some, okay, so center is around 1, so it's not really sure, but maybe around here 1. Okay, and once you observe the f value, for example, f value is here, maybe we observed, so that we write small f, then p-value is the 2 times this area. So basically, this is asymmetric distribution, so we cannot, of both sides. So hypothetically, okay, so how extreme this statistic is, that is, okay, so more extreme situation than this, the small f, happens only when f statistic falls in this range or this range. So if this area is alpha, then we also calculate, we think about the diagonal tail and this p-value for this F statistic is equal to 2 alpha. That is our definition of p-value. So rejection region is the both sides of this F distribution. For example, if the 10% level, and this is the 10th percentile, suppose that is F sub 0.1 of degrees of freedom n-1, m-1, and sorry, for 10% test, if we have, this is the 5 percentile, F of 0.05, and suppose this is also 5 percentile, F of 0.95 up, and rejection region at 10% significance level is, this range and this range. So this area and this area. So this is the sum of this area is rejection region. So in this way, we determine the rejection region. So this is how to do the F test. And one-sided test is also possible. For example, think about the hypothesis that the sigma x is, okay, so sigma x was on the numerator. So suppose that our null hypothesis is sigma x is larger than sigma y, then rejection region was just one-sided. So it's 10% significance level. We take some value, f of 0.9 here. Then suppose this area is 10%. Then this range is rejection region at 10%. The statistic falls in this range around here, we reject. If F statistic fall in this range, then we don't reject F. So this is one-sided test, and of course we can do the other way around. The sigma x is less than the sigma y. Also, we can test that. And here is the R code example for the test for variances. And we can use a new function, the var.test. So if we have one sample, the Detroit test score and the Dearborn test score, then we can just put the 2 vectors here, then we can do variance test here. And if we type this, then the output is this. So at first, F statistic, the 2.54. So F statistic is roughly 1, so 2.54 is rather higher than the median, probably. It's not guaranteed, but intuitively it's higher than median. So the situation is the 2.54 is around here. Maybe 1 is around here. This is F distribution with degrees of freedom. n-1, m-1. So here, Detroit has 7 observations. Dearborn have 5 observations. 6, 4. So density of this F64 is this curve. Then p-value is defined by this area times 2. So suppose this is, say, some number. Okay, so A, then p-value is 2 times A. And degrees of freedom, okay, so degrees of freedom 6 and 4, and the p-value is 0.3855. So that means A is around 0.1927 or 8. So we don't reject null hypothesis because p-value is larger than threshold. Usually we set that 5%, so we don't reject null hypothesis. So at significance level, 5%. So this is an example. And another sample code from scratch. So remember that the F statistic is just Sx squared. And these are sample variances. So we can just calculate this by variance of dt and variance of dB. So remember that the VAR function is sample variance. So we got the same test statistic. So this is F statistics, F statistic. And if you wanna see the rejection region, that is at 5% level. So if the significance level is 5%, then we take 2.5% each for upper quantile and lower quantile. So that means, so rejection region is if we have F distribution like this, this point is 9.19. So this is 0.025. And the other way around is here. So this point is 0.16. So 0.16. So rejection region is here and here. So our test statistic is 2.54. So this falls around here, maybe around here. So we don't reject null hypothesis. If you wanna calculate the p-value, maybe 2.54. Probably this is much, the thinner tail. So 9.19 is much the right than this point. But okay, so 2.54 is probably around here. So p-value is this area times 2. So this area is actually around probably 0.1928 or something. So if we multiply by 2, that becomes 0.355. Yeah. So logically, of course, maybe the lower tail, the lower probability. So probability of F distribution is less than 2.54 is smaller. But intuitively, center is at 1. So 2.54 is on the upper half of the distribution. So we calculate this area directly, and then we multiply by 2 to get a p-value. Yep. So this is a demonstration of the variance test in our language in 2 ways. And this variance, test for variance is often used to compare the 2 different statistical models. The variance usually it means the precision or I would say some error size of the model. So when we want to compare the 2 prediction model and we want to see which model is more accurate, the variance test is often used. We will discuss this in later chapter, in chapter 6, 7, and 11.